So what I thought I'd do is just show you a few examples of how instruments are really used in the experimental field. I always like to show off that at the NEAS facilities in particular, we're building things, we're building real things, we're building using our hands, working with the dirt. In geotech, we're lucky enough to work with dirt, and it's fun. So, but it's real stuff. It's real instrumentation. We really want to learn some things. I've shown a few graduate students here. I'm going to show a bunch of experiments and work by many graduate students. I'm not going to be giving them all credit at the time, but thanks to all the graduate students whose work I am now going to show. That's what happens when you run the facility and everybody comes and does work at your facility, but you're not actually working with all of them. So if you come to a NEAS facility, you're going to find that we have a lot of instruments. We have the capability of measuring lots of stuff. This is just an example of one model we ran. There's MEMS accelerometers, there's piezoelectric accelerometers, there's lots of strain gauges. You see those big bundles of wires coming off with strain gauges. You might have Pore water pressure transducers. There's it's a little hard to see, but there's high-speed video cameras and regular video cameras, and so there's just there's no end to what you can measure. And so usually when somebody comes in, they just want to, it's like going to the smorgasbord. They want to measure everything. And how do you decide what you want to measure? And that's always the first discussion we have, is how do you decide what you want to measure? Because you can't measure everything. Or you can, but it'll take you forever. So I wanted to give you a specific example, and many of you have probably seen this before. This is an experiment we did a couple years ago of the BART tube. I'm not real comfortable standing behind the podium. I like to stand and dance in front of the screen, so maybe I'm loud enough. Do we need the mic for the video, or is? Yes, should be okay. Okay, we should be able. I'll do that. This is a model we ran for the BART tube, and with this model, you can see this is a model of the BART tube, and this is representative of what was really like in the field. The BART tube is built by digging out a trench in the bottom of the bay. And then they dumped in gravels and sands. They sank the tube on top of that, and then they put in more sands, and then over time it's been filled up with mud on top of that. And they're worried that during an earthquake that soil is going to liquefy, and if it liquefies, this tube is going to be buoyant, and maybe it pops out of the ground. And that would be a bad thing for the tube to pop out of the ground after an earthquake. So that's the concern, that's the worry. And so the question is, we can build a model of that, and we can instrument it with all kinds of things. But how do we decide what we want to instrument in there? And so this team, they spent a lot of time studying what it is they wanted to study, right? Before you do a really complicated model, the first thing you have to think about before you build the model is what it is you want to measure. And so they had run many, many numerical models to identify the mechanisms that they thought that they were wondering about. They were questioning what kind of things could be happening in a model. So, for example, one way the tube might move, for example, is during the earthquake, the tube is going to shift back and forth inside that tunnel, or inside the liquefiable soil. It's going to rock back and forth like that. And as it does that, you can imagine the sand kind of filling in behind the tube each time, and it kind of ratchets its way up. So we want to be able to see, that's postulated. We think that might happen. So what we want to do during the experiment is we want to measure that. We want to verify, did that happen or not? So we have to think about, how do we measure ratcheting? Another mechanism might be the bottom heave, the whole bottom of the clay tube. As this tube tries to pull up, you get suction, and you're going to have negative pressures in here. Maybe the whole bottom of the clay actually moves and the tube rises because you have this reverse bearing failure. So we want to be able to instrument for that. One of the big concerns was, and I wasn't going to have the X's on here, but they're on there. Viscous flow of the fluid, right? If the tube just pops out of the ground and the soil is so liquefied that it just flows underneath the tube, that could be some really big movements, and the tube could pop out of the ground. So we want to measure for that. So this is what it actually looked like when we did measure it. Some of the things we measured, for example, you have displacement transducers to measure the ground settlement. There's flags on here and more string pots that are connected to the tube, so we can try to measure the vertical movement of the tube, horizontal movement of the tube. There's Pore water pressure sensors all the way around the tube to try to measure the flow of water around the tube. By measuring the pressure, we can measure the heads, we can measure the flow of water. Water pressure sensors in the soil. There's vertical lines that actually just colored sand columns so that you can excavate it and physically see if the sand moved underneath. You know, it's a very important measurement, the excavation and the physical record of what happened afterwards, as opposed to an electronic reading, just the colored sand layers that we can dig up. We developed these these are electrode sensors. We actually measure the conductivity of the soil and measure the measure with electrical properties. We can measure the separation of these two electrical plates, and then as they move, we could actually measure the movement of the tube relative to the bottom of the clay layer with that. So new sensors that we developed specifically for this project, because we needed to be able to measure relative movement of this relative to the soil, and trying to measure relative displacement buried structures is not an easy thing. So a lot of instrumentation, and this was all developed based on the mechanisms that they're trying to study. And then just a couple of an idea of how much work is involved in putting these things together. The tube while it's going in, and there's a really good picture of the model there. Not on this one, unfortunately. So just showing you this, I just wanted to point out you can see some of the sensors in here and the complexity of the model that goes in. These are pore pressure sensors that are actually buried in the tube. There's the displacement flags and things are on the tube. Everything gets buried in. There's all those little columns you see, the little metal tubes. Those are going to be filled with colored sand as we bury them, and then the tubes will be pulled out, so it leaves behind a vertical line of colored sand that we can then excavate. And then, excuse me, that's what this looks like. And the story of this and the end position is basically, with all of this instrumentation, with this physical model test that we ran, we actually were able to verify with all the advanced numerical modeling that they were done, is that we had a pretty good idea of what was happening, and it was pretty consistent with the numerical models. We had a lot of confidence that they were actually, the mechanisms that they thought were going to be there were there, the mechanisms that they didn't think were going to be there weren't there, and we had all the instrumentation and monitoring in there to be able to verify that. Another point I wanted to make with these models, if you're ever thinking about building a model and instrumenting it, these things, especially at the NICE facilities, they're advanced models. They're team-based efforts. So this is another project we're doing. It's ongoing right now. And with this project, they're looking at the performance of a urban environment. So response of one building, the building-soil-building interaction. And so the response of one building on the behavior of another building. It's pretty difficult to measure, and it's pretty subtle. And so you actually have teams of geotech engineers. You have Ben Mason from Berkeley there, who is the lead geotech engineer. And then on the other side, you have Nick Trombetta from San Diego, who is the lead structural engineer. And then each of them are designing all of the instrumentation. You can see Nick's model of the structure there. That's a multi-story structure with a basement and all the strain gauging that's going on there. They're complicated designs. They're, like Bob was saying, making sure you're within the operating range for the phenomenon you're trying to measure is critical. And so it's a big design process that goes in long before they're ever building these things. The other thing to think about with a model like this is every one of those strain gauges, it's probably a $400 application by the time you figure in the installation and the connectors and the wires and the labor of actually installing that thing. And so if you have that structure had 70 or 80 strain gauges on it, you know, you're in a $35,000, $40,000 structure. They're not cheap little things that you run down and just do a test because you think you want to do a test. I was going to kind of skip through that, but one other point I want to make on this, even on our small centrifuge test, people tend to think they're small centrifuge tests, so it goes pretty quickly. But this is a real centrifuge schedule. I just wanted to point out the August 9th, the researcher was planning on putting the model on the arm, and August 16th, August 17th was the first day they were going to spin. So an entire week of just plugging in wires and making sure all the instruments work, and that's for about 200 sensors. And then, just so you have an example, and how much time do I have?
About 5 minutes.
Perfect. So this is what the model looks like when it's ready to go, and there's I think about 180 transducers on this model, all the various instrumentation coming off and being plugged in. Maybe this is cleaner than Bob's example. Maybe not. I'm not sure. There was an awful lot of work by a big team of researchers to get to this point. And then, as Bob mentioned, the reaction frame is what I have this picture in here. You can see that looking down on the structures, and we have all the displacement transducers just like Bob was showing, and a reaction frame. And of course, in our environment, it's even worse because this is designed to go up to 50 Gs, 60. I think this was at 65 Gs. So the reaction frame not only has to handle the shaking, but the static G load as well. And everything has to be engineered. It's not just simply stick it on there and hope it's stiff enough. Because if it's not engineered, I'll guarantee it's going to vibrate. Then the last thing I wanted to show, and there's a really nice little video that goes on the left-hand corner, which was working before, so I'm not sure what you guys did to it. I tested all this before I came in here, so somebody messed with something. I'll show you a video in the afterward session. This was a model we did with looking at liquefaction, remediation, and drains. And what I really like about this with this picture, the video is a nice flavor, so it makes it less boring when you're listening to me. We had an awful lot of instrumentation. There was 60 pore pressure transducers in this model. Okay, each pore pressure transducer is about $1,200. And there was another 40 or 50 accelerometers, which again, the accelerometers are $500 a piece. So you're looking at $80,000, $100,000 worth of instrumentation in the soil in this model. When they get this kind of a dense instrumentation array, you can do some really neat things with combining the data from different sources and doing some really neat calculations. And that's what this is. This is a highly processed piece of information here. But what's neat about this is you can see with this is a slope, so they can measure settlement and lateral spreading of the slope. And that's what you see at this top curve is lateral displacement and settlement. Then you can look at excess pore pressures, and we're all used to looking at excess pore pressure and liquefaction. You know, it liquefies and the pore pressures stay high, then it starts to drain. What we don't typically look at is this curve, which is a volume flow of water. If you have a whole bunch of pore pressures like this, you can look at the hydraulic gradients and you can calculate volume flows of water. Now, if you talk about the volume flow of water, you can start correlating. You know, as the volume of water flows out, that means the soil has to be settling. The volume of the soil is changing. So you should be able to correlate this volume flow of water with vertical settlement. And you can see little subtle things like the volume flow of water increasing, then all of a sudden it comes back in, and little things like the settlement, you know, it stops when the volume changes, and then you have this little jump here, which is the same as that jump. And then you correlate in the end of shaking, start of boiling, end of boiling, which if you had the video, you'd be able to tell. And that's correlated in with the high-speed video cameras. So when you start combining the displacement sensors, the pore pressure sensors, the accelerometers, the high-speed video cameras, all these different data streams, and they all tell the same story, and they all need to tell a consistent story. And they used all of that information to study the mechanisms that they were interested in.